So let's take a moment to talk about the properties of matrices. In previous math classes, you guys learned about all the different properties of regular old scalar numbers, like the commutative property of addition and the associative property and all that stuff. We'll do a quick review of that as we're going through and seeing, do these properties apply to matrices as well? So usually the first one that people learn is the commutative property. So let's go ahead and talk about the commutative property. Specifically, let's look at addition first. So in case you've forgotten, the commutative property of addition basically says that 4 plus 3 is equivalent to 3 plus 4, because both of those are 7. You're allowed to interchange these however you want, and you'll end up with the same answer. So let's go ahead and take a moment and see if that works for matrices as well. So let's check it for the addition. We'll get negative 3 plus 5. Negative 3 plus 5. And then in the next entry, we get 4 plus negative 6. And we get negative 2 plus 3. And we end up with 1 plus 2. And we can go ahead and simplify those down and get an answer. But let's go ahead and take a moment to pause and do it with the other way. So if you'll notice, I've just switched the order of these matrices. So 5 plus negative 3, negative 6 plus 4, 3 plus negative 2, and 2 plus 1. So if you go through and you add these and figure out the final answer, you'll actually find out that they equal each other. And if you look carefully, you can see why. We've already established that the commutative property of addition works with just numbers. So if you look at each entry is its own example of the commutative property of addition. You're simply just changing the order of those entries. So it's really not that big a deal. When you add matrices, you can add them in any order you'd like. Rearrange them, go through, mess with it, do whatever you need to for addition, because you'll end up with that same answer. So let's go ahead and take a moment to see if this works for multiplication. With regular numbers, commutative property of multiplication does apply. So using that same example that we used before, 4 times 3 will be the exact same thing as 3 times 4, because both of those will equal 12. With regular numbers, you're allowed to mix up those numbers however you want, and you'll still get the same answer. So let's take a moment to see if that applies to matrices. So with matrices, remember, in order to get this first entry, we need to do row 1 and column 1. So negative 3 times 5 plus, we've got a second entry here, 4 times 3. And this would be our row 1, column 1 spot. So we can go through and we can figure out this whole matrix. But really all we need to find out is, are these the same answer? So I'm just going to compare the first entry. If the first entry is the same, then I'll keep going. If it's different, then I know that I can stop. So in this case, row 1, column 1, we do 5 times negative 3. So far we're off to a good start. Plus, and it's row 1, negative 6 times negative 2. Oh, and we start getting things that are a little bit different. So maybe something still happens and we're all good. So let's go ahead and actually figure out what these numbers turn into. So negative 15 plus 12. Negative 15 plus 12 gives me negative 3. And then down here we've got negative 15 plus, we've got a positive 12. So again, we're off to a good start. Okay, I'm all right with this so far. We end up with negative 3 on both of those. Let's go ahead and find out with that second entry. So row 2, let's look at row 2, column 1 now. Row 2. So negative 2 times 5 plus 1 times 3. And down here we'll have 3 times negative 3 plus 2 times negative 2. And we get negative 10 plus 3, giving us negative 7. And here we have negative 9 plus negative 4. Oh, and now we have a different answer. So if this was my first time doing this, I would double check to make sure I didn't make a silly error. but it turns out that the commutative property of multiplication does not work for matrices. So that's actually a very, very important thing to remember, is that you can add matrices in any order you want. So if you have matrix A plus matrix B, you are more than welcome to change that to B plus A. What you cannot do is you cannot say that A times B is equal to B times A. This is untrue, and those are not equal. You can actually do a very, very simple proof of that just by looking at the order of the matrices. So when you're multiplying matrices, one thing to keep in mind is that if you're multiplying a 3 by 2 times some other matrix, the columns of this matrix has to equal the number of rows in this matrix. So this is a totally allowable thing to multiply because you've got the columns of the first matrix equaling the columns of the second. Sorry, equaling the rows of the second. But if you switch those two around, then you'll end up with a 2 by 4 times a 3 by 2. In which case, because these columns don't match these rows, this one's not even possible. So in this case, you are allowed to multiply them, but in these, it's not even possible. So this right here proves that the commutative property of multiplication does not apply to matrices. So let's go ahead and take a look at the next property that you look at. Next property that you people tend to learn is the associative property. The associative property talks about when you are adding or adding or multiplying numbers. So as an example, you can do something like 4 plus 8 plus 2 for the associative property of addition. Many people would go through here and say, well, let's first add these numbers, and you'll end up with 12 plus 2, and then you'll end up with 14. But what the associative property says is you are more than welcome to add these two first. As a matter of fact, some people might find this way a little bit easier, because 8 plus 2 is 10, and you'll end up with 14 again. So this is that associative property of addition. You can group them however you want. So what I would encourage you guys to do is take a moment and try and add them like this and get an answer, and then add them where the parentheses are around these two instead. What you'll end up discovering is that they are exactly the same answer. The associative property of addition does hold true for matrices. We can actually do the exact same thing with multiplication, and again, it turns out it is true. So when you're adding or multiplying matrices, the order in which you do them, so how you group them, does not matter. You can group them however you want. If you've got matrix A times matrix B times matrix C, that is equivalent whether you do this way first, or you can do B times C first, and then you'll end up with the exact same answer. This is a true statement. As long as you don't change the order of these as you move them around, as long as you don't rearrange these matrices, this is totally true. You can have 100 matrices that you're multiplying together, and it doesn't matter how you group those matrices as long as you don't change the order of them. So associative property does work for both addition and multiplication. The next important thing that we're going to talk about is the identity. And this is kind of a weird one in terms of regular numbers. It's one that you actually don't talk about very often, and for matrices we'll actually only talk about the multiplication identity. But for those of you who are interested, the identity property is basically saying if you take some number and you multiply it by 1, you'll get that number back. So the identity for that multiplication is just 1. Now, one thing you can't do in matrices, and this is the first thing that everyone wants to try, is you're told there is some matrix that you can multiply by. There's some matrix that you can multiply this matrix by and get the exact same matrix out. The first thing everyone tries is to make a matrix filled with 1s. And you'll quickly discover that that doesn't work. A matrix filled with 1s ends up giving you a completely different matrix. So this is not the identity matrix for matrices. The identity matrix is actually this right here. the identity matrix has to be a square matrix, so it must be a square matrix, which again, in case you've forgotten, it's where you have the same number of rows as columns. So let's go ahead and say A by A. Doesn't matter what A is. It could be 2, it could be 4, it could be 12, any number as long as the number of rows matches the number of columns. The other stipulation is that the main diagonal is filled with 1s. So you'll see right here, this is a very basic example, and I'm going to go ahead and prove it to you. What should happen is when I multiply these two matrices, I should get this one back. So negative 3 times 1 plus 4 times 0. And then down here we've got negative 2 times 1 plus 1 times 0. In the next entry, we've got 4 times, oops, sorry, I got lost here. Row 1, column 2. Sometimes I get lost as well. That's why I like those little lines. Negative 3 times 0 plus 4 times 1. And then down here, we've got negative 2 times 0 plus 1 times 1. Doing the math, we end up with negative 3. Down here we have negative 2. And then we've got 4 and 1. So this is that identity matrix. I can expand it if I want to. I could make a 6 by 6 identity matrix. And I do so by putting 1s on all the main diagonals. So 1, 2, 3, 4, 5, 6. 0. There's 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And last but not least, all zeros there. This is a 6 by 6 identity matrix where you have that center, or sorry, the main diagonal all being 1s and everything else is 0. You can make it as big or as small as you want, and no matter what, as long as you multiply it by a proper matrix, you will get that original matrix back out. So that's what's special about the identity matrix. It's used in a lot of things, almost as a way of kind of cheating to get rid of and do a little bit of division in matrices. The last property we're going to talk about is the inverse. So matrices have inverses. In case you've forgotten, for regular old numbers, you can say this right here. You've got some number that you can multiply it by to always get 1 back. So in this case with matrices, remember there is no 1. It's the identity matrix. So what this property is saying is there's some matrix that I can multiply by to get the identity matrix back. Something that I can multiply by to get the identity matrix back. And we have actually discovered an equation for that. Real quick, let's give you a little bit of background here. Let's define some matrix A. And instead of saying A11, A12, all that kind of stuff, let's just call them lowercase a, b, c, d. That'll make our lives a little bit easier and make the equation a little bit nicer. So if we wanted to find the inverse of this matrix, we can denote it by an a to the negative 1. And we end up doing 1 over a times d, so this left to right diagonal, minus b times c. And then that gets, with scalar multiplication, we're going to put it in there, but we're going to multiply it by slightly different, what I call a modified matrix. Instead of a, b, c, and d, we're going to switch a and d, so d and a, and then we change the signs of b and c, so negative b and negative c. Again, something to keep in mind is it's not changing it to negative, it's changing the sign. You're multiplying that number by negative 1. So let's go ahead and do that with this matrix right here. So I have this as my matrix A. To find the inverse of that, it's going to be 1 over a times d, 5 times 2, minus b times c, negative 6 times 3. And that gets multiplied by my modified matrix here. So I'm going to switch a and d, 2 here, 5 there, and I change the signs, or I multiply it by negative 1. So negative 6 becomes positive 6, positive 3 becomes negative 3. Doing a little bit of simplification, 10 minus negative 18 2, 6, negative 3, and 5. We end up with 1 over 28, 2, 6, negative 3, 5. Using scalar multiplication, 2 over 28, 6 over 28, negative 3 over 28, and 5 over 28. Now at this point you should definitely make sure that you simplify, which will give us an inverse of, well, I see a 2 in common there, so 1 over 14. Here I see a 2 in common, so it would be a 3 over 14. Here I don't see anything in common, and here I don't see anything in common either. So there is my inverse. And as a little exercise for you, what I would strongly suggest doing is taking a moment to multiply the original matrix by its inverse. You can guarantee that you're correct if you get that if you get the identity matrix here, because that is the definition of an inverse matrix, is a matrix times its inverse will give that identity matrix back. So that is an overview of the 4 main properties that we're going to be looking at with matrices.